Let's continue with the test review with chapter 18. So the next part here says find electric potential at a point. So this is talking about how if you have a charge, well, it produces a potential. So as you're a certain distance away from it, it produces a smaller and smaller potential the further and further that you go away from it. So you would use this equation right here. So let me erase all this. You would use this equation right here. So this would just be kind of a plug and chug kind of thing. And if you have more than one charge, then potential is a scalar, so you don't have to worry about direction. But let's say you have a negative charge here, and it produces a potential at this point. So you'd have to find, this is charge 1 and this is charge 2. So at this point right here, it would be a potential due to charge 1 plus a potential due to charge 2. Now the potential due to charge 2 would be negative since the charge is negative, but you would just add the numbers, technically subtract the numbers, but there's no vectors involved. And then we move on to capacitors. So I ended up not mentioning this one here on the test review, so don't worry about this equation. And so capacitance here, we have two equations for it. So first of all, this one means that the capacitance depends on the area of the plates and on the distance between them. So we're talking about a parallel plate capacitor that has two plates and they're a certain distance d apart and they have a certain area, and those two factors affect the capacitance. And capacitance is also a measure of how much charge that the plates can store for a given potential difference. So what this means is that if you hook up these plates and charge them up, let's say there's a power supply here, and if this was 9 volts here, then after it's connected, then you're going to have the 9 volts across the plates here. So that means they're going to have build up some charge. So the greater the capacitance, then the more charge they can hold. That's what the equation Q's over delta V stands for. Plates have equal and opposite charges, so it's talking about this Q is talking about the charge on one plate, so this plate is positive, this plate is negative. It's the same amount of charge on each one. And then if you stick a dielectric material in between the plates, then it will increase the capacitance. So the equation that relates to this is right here. So you could rewrite this as C equals kappa times C0, C0. So this is the original capacitance, and then kappa is the dielectric constant, so the property of that material that you're putting in between the plates. It's going to be a number greater than 1. And then you multiply it by the original capacitance, and it gives you the new capacitance, which will be a bigger number. And let's look at the properties of capacitors in series and in parallel. So these equations here are reminding us of, these bullets here are reminding us of what these equations here are saying. So if your capacitors are hooked in series, right, so series looks like this. You have a circuit, you got some kind of battery here, over here's a battery. These two capacitors are in series. They can be drawn like this, or they can be drawn like this. As long as you can make just one loop, go from one terminal of your battery and go do that one loop and go to the other terminal of the battery, there's only one option for that loop, then these are going to be in series. So you need to be able to identify, if you are given a picture, you need to be able to identify, are these in series or are these in parallel? And then you need to be able to apply these equations. So the charge is the same on capacitors in series. So that means that if you know that this one is holding 100 microcoulombs of charge, then you know that this one here is also storing 100 microcoulombs of charge. They all store the same charge. And the equivalent capacitance is less. So that's talking about this equation, right? If you know the capacitance C1 on this capacitor and the capacitance C2 here, and then you're trying to simplify this circuit into one capacitor that has an equivalent capacitance, well, by using this equation right here, this would be C equivalent right here, and plugging in the numbers and solving for C equivalent, you'll get a number that is smaller than either of the two original capacitances. So this is basically just giving you some conceptual ideas based on the equations. And I didn't mention the last one, but you're going to have to use this equation as well. The voltages add up if you're in series, so that means that if you know that there were 9 volts here and that there were 4 volts across this capacitor, then there would be 5 volts across this capacitor. They have to add up to the total voltage provided by your source. And then you need to be able to identify series in circuits in parallel. So in parallel, the common diagram is like this, where this is your battery and these are your two capacitors. And you can see that there's a direct path from one plate to one end of the terminal, to the other plate to the other end. And the other capacitor also has that path. So they're both hooked directly to the battery. That's one way of thinking about it. So those would be in parallel. And once again, if this had been drawn like this, oops, this had been drawn like this, these would still be in parallel. We talked about it doesn't matter if the capacitor is here or right here, because you can move it as long as you're not moving it through a junction, through a bunch of wires here. If you have it here, then this plate is still hooked. There's still a straight path to that terminal, and this one still has a straight path to that one. These would still be in parallel as well. And then you would go to this set of equations for the parallel capacitors, and it tells you that if you were to simplify the circuit into one capacitor, then the equivalent capacitance here would be the sum of the individual ones, so it would be a greater number. Potential difference across each capacitor here, this delta V is the same as this delta V is the same as this delta V. And then the charge on each capacitor add up to the charge here on the equivalent capacitor.